Welcome to Mathsplain, a web video series dedicated to helping those who need help with math, where I explain the math for you. So without further ado, let's just jump right into it. In this episode I want to cover all the math that I know of. So we're just going to go quickly over it, and I hope that you will learn something. Alright, let's start with the absolute basics. As you can see, I drew some shapes here on the screen, and your exercise is it to now tell me how many shapes there are.
4, 3, 2, 1, 0.
So, how many shapes are there? Well, of course, it's 7. And how did you figure that out? Well, what you basically did was you started counting. That's right, that's the first operation in basic maths. It's counting. Like 1, 2, 3, 4, 5, 6, and 7. So we know it's 7 different shapes. That's why we wrote down 7. What I now did was I modified the shapes that we just had and colored them. What I want you to tell me is how many different colors there are.
3, 2, 1, 0.
So there are 3 different colors. Again, we start counting. So we have yellow, which is these 2. We have blue, which are these 2. And we have orange, which are these 3 over here. Alright, next up I want to talk with you about some of the shapes we have here. In math, we tend to work with shapes. Now, these 3 shapes here, for example, are fundamental mathematical shapes, which we can use to determine and figure out certain information. How do we do that? Well, for that we need numbers. Now, how are these shapes called? Well, let's start with the shape on the left. I want to know how many sides does this shape have? Well, let's just get counting. It has 1, 2, 3, 4. This shape has 4 sides and it's called a square. Alright, how many sides does the next shape have? Well, let's just get counting again. 1, 2, 3. That's 3 sides. How is this shape called? That's right, a triangle. Why a triangle? You see, an angle is something that is a bit more complicated. But what all you need to know right now is that an angle lies between 2 lines that meet, and that there's a certain number which can be used to describe this difference. And this number at this spot is called an angle. Now, what is the last shape called? It has 1 side. That's right, it's called a point. Because it is a point. It only has 1 side. It's round like a point. Or you could also call it a ball if you want to. Now, after learning a bit more about the fundamental shapes, let's go over the fundamental numbers that we deal with. I want you to count with me from 1 to 9. So that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. What comes after 9 is actually 10. Now you might have known that, but why does the length of the number increase as soon as we pass 9? Well, it's because these numbers are here are the single digits. They're 1 digit. Now you might be wondering, well, what is this funky thing over here? where does it belong? Well, when I asked you to count from 1 to 9, I deliberately left out this weird number. This number here is called the 0, and it is a very important number that we get to later. All you need to know is that these numbers go from a 1 to 9, and as soon as the 9 is passed, we are in the 2-digit zone, where we add a 1 in front of a 0, and then the 0 starts to count up. So basically the 0 would be replaced with a 1, then we have 11, then 2, then we have 12, then a 3, then we have 13, and so on. Until we pass 9 again, at which point there's a 2 in front and it goes back to 0. This is how you count above the single-digit area. And the pleasant thing is that if you understand this rule, you can actually go on counting upwards and always apply the same rule. Now, as soon as there's a 9 in front of the second digit, once you add one more, you count up one more, you just add a 1 here and the other two go to 0. So basically, this is how you count upwards. For the remainder of this video, I want to change a bit because this makes it a lot more complicated. Remembering all these different digits is not an easy task. So what I'm proposing to you is that we're just gonna get rid of the 5, 6, 7, 8, because these numbers kind of are in our way. So from now on, I will begin counting at 1, then go to the 2, then go to the 3, then go to the 4, because those are the first 4 digits, and then go to the 9, because I don't want to talk about the 5 to the 8, and then we are at the 0, and this first digit goes up to the front, and we just forget about the 5, 6, 7, 8. So this makes it more simple. Okay, the numbers remain smaller and we can talk about simpler ideas. So, how do we go on from here? Well, we have already talked about how counting upwards works, and I have already used one term that is very important in mathematics. It's to add another number. How does that work? What do I mean with that? Well, basically all numbers we have in our current number system are along a line. This line right here. Basically it's like a huge chain where all of the numbers are intersected. And usually we start at some point. For example, let's say we start at the 3. And from the 3 we're gonna go to the 9. So in this case, as you can see, to go from the 3 to the 9, I would have to bypass 4 and then go to the 9. How many steps is that? Well, it's 2. Just count. 1, 2. Perfect. So what we're doing here is going one step each time. And what we can do with these 2 steps is that we can count them as 1, which makes them 2, because we know we start at 1 and go 1 further to the right and end at the 2. So 1 and another 1 is 2. Now, for those of you who have already passed the first grade, this might seem like some sort of ridiculous idea, or it's redundant and you're already very bored. But what I'm describing here is addition. That's right, addition. When you use addition, you have a number. For example, the 3. You then add the amount of steps to get to another number. So, what have I written down here? It's basically a very interesting way to write this main operation down. I have started at the 3, which is the number we started at. Then I'm making this operation that basically just says I'm changing something, I'm doing something with the number that I've selected. In this case it's addition. Behind that I have 2 brackets in which I put the number that I want to change 3 from, and then the result, which is this arrow here, becomes a 9, because we have left out all the other numbers from 5 to 8, and we're not gonna talk about them, so stop addressing them, stop thinking about them. Okay? Now, over the course of history, mathematicians have tried to figure out how to simplify this way of writing this down. And there's this commonly accepted form that looks like the following. What we're basically doing here is simplifying what I've written up there. We started at 3, which is the first digit, then we have this point which basically says we want to change the 3, in which case this is addition. And addition uses the plus sign. You might have seen this already a bunch of times. Then the parameter of the function, which is the addition, goes behind the plus. Then we say that this turns into an equal sign. Now an equal sign means that whatever is on the left and the right side of the equal sign is the same. And then we have the 9, which is the solution to the problem. So in case you haven't figured it out already, addition always does one thing. Pick a number that you start from, then you move a selected length to the right in order to arrive at your destination. And the length to the right is what you add to the 2 in order to get to the solution. But what if I don't want to go to the right? What if I want to go to the left, you might ask? Well, let's just ask ourselves that. What if I would be at 11 currently, and I want to go to the 4? Well, in that case, you'd have to do something that is not addition, but the reverse way of addition. In case you weren't sure what I meant with my message from before, here I wrote it down again in the correct way to write it down. So we start at the 11, want to change the number. We want to go to 4, which is the last step here. And in order to do that, we have to do something that is called subtract. And how much do we subtract? 3, because we want to go from 11 to 4. Then it's 10, 9, 4. Here is the old way of writing it down, just in case you aren't used to it. And here we have the drawn out and visualized proof that actually if we go from 11 to 4, we have to subtract 3. So, in order to summarize, what have we learned now? It is that when we want to change our number from our current number, which might be any number on this line, let's just say the 20, and we want to go to the right of it, we have to count upwards. Counting upwards means addition, and we need the information of either our destination or the length, so that would mean the amount of steps we'd have to go in order to arrive at the destination. So let's just say we want to go from 20 to 30, then that would be an addition of 6. Likewise, if we want to go to the left of 20, let's just say we want to go to the 4, then we'd have to subtract. So in that case, we have again our starting position, which is 20, and we want to go to the 4. In that case, we have to go to the left by subtracting, in this case, 8, because we go 8 steps to the left. One big important step when wanting to learn math is to apply what you've learned. So I wrote down 3 exercises, and while I briefly go to the toilet, you hopefully have enough time to finish these and find the solution for the problem. It's not that complicated. I'll be right back, and I hope that you will have a solution by the moment I'm back again. So I'm back, and as I can see, you have not figured out the solutions to the problem yet, but no worries, we're just gonna talk about them, and you will probably learn a lot while also listening to it. So first up, 10 minus 2. That is quite easy. We start at the 10, go 2 backwards. That's what you could have also done in the video. You could have just scrolled back if you had problems and look at the solution. If we start at 10 and we go 2 to the left, then we're at 4. So the solution to the problem is 4. Next up, 4 plus 31. Now we have to be very careful here. 4 plus 31 does not mean that we go to 35. We cannot go to 35. I've cut out the 5, so that's not possible. Where are we if we start at 4 and go 31 to the right? Well, let's count, shall we? So, if we want to count, we have to go 31 steps to the right. We start at the 4 and we're just gonna go, okay? So that's 1, 2, 3, 4, 9, 10, 11, 12, 13, 14, 19, 20, 21, 22, 23, 24... Well, shit. So 4 plus 31 is equal to 39. And last exercise, 10 minus 12. What is that? Well, let's just count. 10 minus 12 is equal to 1, 2, 3, 4, 9. Oh. I need to introduce the numbers. So, what is to the left of 1, our starting number? This is quite a complicated question, actually, because usually when we count something, it's equal to the amount of objects we have of something. Well, if we don't have a single object, then we have something that does not exist. So, let's just say that we have an apple, right? And we take that apple away, then we have nothing. Right, so there's some sort of void left to the 1. But what is left to the void, to something that we don't know what it is, because it can't be? Well, to the left of that is actually something rather interesting. Now, scientists and mathematicians have tried to figure this out for ages, right? But what they have concluded is that whatever is left of the 1 functions basically as a mirror. So we have our 1, and then to the left of that is this so-called mirror thing. We don't know anything about it or how we could use it, but what is left to that is our new 1. It is another 1, and to the left of that is a 2. So basically, from how it used to be, that our 1 is the leftmost object, and then we go to the right and the number increases. Now we are basically reversing this order by making the 1 the rightmost object. And to the right of that is our basically mirror or portal, as some have also speculated it could be called. And to the left of that 1 is the 2. These numbers over here are called the mirrored numbers, because they are within this mirror reversed realm that we have yet to explore more from. So what's the solution to this problem that brought up this question? Well, of course, it's mirrored 3. I guess that explains itself, doesn't it? But in case you didn't quite get it, let me visualize it so we can actually agree and be on the same page here. We should count this, right? We go 1, 2, 3, 4, 9, 10, and then 11, and then 12 to the left. So our outcome is at mirrored 3. let's further add to what I have just explained to you with the new addition of mirrored numbers. The old way of trying to describe the mirrorplex, as some call it, which is this weird area left to the original one and right to the mirrored one, was a 0, which has been debunked. It is false, it is not correct to do that, but we have, as a mathematic organization, agreed to use this symbol as a replacement for what usually used to be 0. This symbol shows that it is not 0, but at the same time can be used in order to describe whatever is here. The biggest mistake you could make is to count this number. This number does not exist. It cannot be, so therefore avoid it and go one further than that. I now want to talk about using variables and symbols that aren't part of our digits in order to solve problems. In order to do that, I will write down an example. Here's one example of how to notate a problem which you haven't figured out the solution for yet, but you want to go at it. If a problem looks like this, then basically all problems have been solved for at this point, because you have all of the information on the left side of the conversion error, and on the right side you have the solution. All you have to do now is solve, or as some people like to call it, shorten the answer on the left, and you will find out what is on the right of the conversion error, what is equal to I in this case. If you followed all the rules, then you will know, oh, that makes sense. 4 add 9 is equal to 13, so 13 is the conversion for I. Again, another problem. You have to figure out what the solution is, and I will tell you in just 5 seconds. So, of course, the solution to this problem is and conversions to I without a problem, without a doubt, if you add 1. What I haven't mentioned here is that instead of it writing addition, I wrote down add, which you can also do. It is a shortened form. Most scientists have agreed that this form is legal and is allowed, so you shouldn't worry about it. So this exercise has a few changes from what we usually had. I just want to make sure, with the change of the I to a J, that every letter is allowed to be used. We usually use an I or U, which is also quite common, and the most common of course is P. P, as always, stands for the number we don't know. It's usually the letter you use. And in this case, I want to know from you what 10 sub 10 converses to. What is J? Now, if you have listened to the explanations that I've given throughout the video, then this should be no problem. Of course, mirror to 1 converts to J. Now, here's something that I am actually not allowed to show you, but I need to talk about this because this is a problem still to this day, and we have to figure out how to stop this, okay? If you see a problem that looks like this, then you have to go to the police and tell the police exactly what you saw. Okay, I just want to make this clear. If someone does this, then you have to report it and you have to tell the police exactly who it was. I'm not kidding. This is an illegal move. This is not allowed. In case you see this, please do the science community a favor and just make a clear cut through it. This is the only solution that is allowed in order to tackle this problem. That does it for the first episode of Mathsplain. I hope you learned something, and I hope that you check out the next episode where we go over some basic operations with mirrored numbers and multiplication and division, as well as a new operation that has just been discovered. I hope you are as much excited as I am, and I'll see you in the next episode. See ya.